This lesson is on mass energy equivalence and deals with page 12 to 14 in the notes. All right, mass energy equivalence. What's the deal with E equals mc squared? Mass energy equivalence tells us that anything that has mass has an equivalent amount of energy and vice versa. This gives us the famous Albert Einstein equation E equals mc squared. In other words, mass can convert to energy and energy can convert to mass. You guys learned this last year in Regents Physics. All right, conservation of mass energy. So we learned about conservation of energy, conservation of mass. It's actually mass energy that's conserved. The total mass energy of a system must remain the same. Mass energy equivalence holds true for all interactions, physical, chemical, nuclear. It's a misconception that it's only true for nuclear reactions. In actuality, it applies to any exchange of energy. However, the amount of mass is usually very, very small because the mass is equal to energy divided by the speed of light squared. And the speed of light squared is a really big number. So a little bit of mass gives you a lot of energy. And a little bit of energy gives you basically very tiny amount of mass, almost zero mass. Um, so a couple things to deal with E equals mc squared. Particle-particle annihilation. When a particle meets its antiparticle, the two annihilate and become pure energy. The opposite of that is pair production, where we use pure energy to create matter, but whenever a particle is created, an antiparticle is created too, because of conservation of charge. So if I have two opposite particles, they annihilate and become energy. And if I start with energy, I can create two opposite particles, a particle and its antiparticle. So what is an antiparticle? Antimatter is the same as regular matter, but with opposite charge. So an antiproton is not an electron, it's a negative proton. It would go in the nucleus of an atom. An antiproton has a charge of -1 elementary charge, but the mass is the mass of a proton, 1.67 times 10 to the -27 kilograms. An antielectron is also called a positron. It's positive. It has a charge of +1 elementary charge, but it has the mass of an electron because it's an electron but positive. And then the antimatter annihilates when it comes in contact with ordinary matter. So where is all the antimatter? This is a crazy question in physics. We can create matter in a lab, but every time we create a proton, we make an antiproton. And every time we make an electron, we make an anti-electron. So when the universe was created, there should have been an equal and opposite. There should have been an equal amount of antiprotons, but we can't seem to see them anywhere. And we would be able to tell if they were out there because if any protons were meeting antiprotons in some like distant galaxy, we'd see them annihilating and becoming pure energy. So nobody knows. That's a big question in physics where the antimatter is. Right? What is energy? How much energy is there in antimatter? What is antimatter? Um, Here we have 1 kilogram of gasoline is 45 million joules, which is a lot. But 1 kilogram of uranium is a lot more. That's 8.1 times 10 to the 13 joules. That's a lot more. Hydrogen's even more, but matter, antimatter just puts them all to shame. It has so much more. It gives 100% of its mass to energy. Here to give this an example, the largest man-made explosion was the Soviet Tsar bomb. 50 megatons of TNT. They were going to make it 100, but they were worried the plane wasn't going to be able to escape. The bombs dropped on Hiroshima and Nagasaki were less than 1/1000th as powerful. This is the same as 4.4 billion kilograms of gasoline, 2,500 kilogram uranium bomb, a 310 kilogram hydrogen bomb. I put a star there because that's what it was. It was a hydrogen bomb. And you could do the same thing with 1 kilogram of antimatter, which is just crazy. So where does nuclear energy come from? This is the mass defect binding energy. When protons and neutrons come together to form a nucleus, it's observed the actual mass of the nucleus is less than the mass of the individual particles, which is kind of crazy It's like you have a 1 pound object, a 1 pound object, you stick them together and it's 1.5 pounds. It's like, where'd the rest go? The missing mass is known as the mass defect. A small quantity of the mass of the particles is converted into binding energy to keep the nucleus together. So that's where it goes. Questions. I suggest you guys try the questions on your own. So pause the video, try the questions, and then resume the video to check your answers. All right, here we go. Number one, for which reaction is E equals mc squared appropriate? Chemical, nuclear, antimatter, all of them. They're all E equals mc squared applies in all of them. True or false, in a nuclear reaction, 100% of mass is converted to energy. It's not. When we split a plutonium or uranium atom, you get smaller atoms, so we still have some of that mass. Or in the sun, we take hydrogen and fuse it together to form helium, but there's the helium there. So the helium weighs less than the hydrogen, and the missing mass becomes energy, but there's still the helium. So less than 100% of the mass is converted to energy. Speaking of the sun, the sun fuses 4 hydrogen atoms into 1 helium atom. Let's figure it out. I mean, it's all in front of you, but let's do it. So hydrogen has a mass of 1.01. Helium is basically made from 4 hydrogen atoms, so you'd expect it to be 4.04, but we're missing 0.04. That's the missing mass. That's the mass defect. Um, so we take that 0.04 atomic mass units, convert it to kilograms. It's 6.64 times 10 to the negative 29 kilograms, which is between the mass of a proton and the mass of an electron. How many joules of energy are released? So we do E equals mc squared. We take that mass, we put in the speed of light squared. It's 5.976 times 10 to the negative 12 joules. And that's in just one reaction. The sun does this 6.44 times 10 to the 37 times per second. So yeah, that's a lot. And then we get a lot of watts out of that. When an electron meets a positron, they annihilate and emit 2 photons. Determine the energy and the frequency. So it's E equals mc squared. The 2 is because it's an electron and a positron. There's 2 things. Then we put the mass. It's the mass of an electron, 9.11 times 10 to the negative 31. The positron has the same mass. That's why we're multiplying by 2. Times the speed of light squared. We get 1.6 times 10 to the negative 13 joules. This actually creates 2 photons, so we're going to divide that in half. We get 8 times 10 to the negative 14 joules for each photon. And then you can do E equals HF and find the frequency. It's 1.2 times 10 to the 20 hertz, which is gamma ray. Here we go. Whoops. A gallon of gasoline has 120 million joules of chemical energy in it. Why did nobody find any missing mass when the gasoline was burned until the 20th century? Do the math. So here's the math. We're doing E equals mc squared. We put our 120 million joules in for E. We're solving for M. We get 1.3 times 10 to the negative 9 kilogram. That's a billionth of a kilogram. So nobody noticed that gasoline lost a billionth of a kilogram until we got to the 20th century and we're able to do this on the finer scale.